All right. Welcome to the Chapter 5 Homework 1 review. So there are 2 assignments in Chapter 5. This is the first of the 2 that went over mostly just mole conversions, as we'll see. Not as much with stoichiometry, which is coming a little bit later. The class average on this assignment was 9.41 out of 12, a little bit lower than last year, but not a bad result overall. And so I'm going to go through several questions here that were either suggested by your fellow students or that I identified from Blackboard as being ones that we have particular difficulty with. So as you saw in this assignment, we took a pretty abrupt change, a pretty sudden turn in the course where we're now doing a lot of numerical type problems, calculating amounts of substances, and a lot more math heavy than it was before in the first few chapters of the course. All right, so let's get into it then with the first one. So one of the things that we had to be able to do on this assignment was we had to be able to calculate molar masses, which can also be called molecular mass, formula mass. There's a lot of ways of naming that, but essentially it's like the mass of 1 mole of compound in grams. So here we had sort of an abstract one where we're using mostly fake elements. So we have, this was a variable input type of question, so the formula of your compound was likely different, the atomic masses that you were given were likely different, but the approach would be the same. So we have a compound with the molecular formula M3XO4,4, and if we have the atomic mass of M is 105 and that of X is 36, what is the molar mass or formula mass of this compound? Alright, so again, for doing formula mass or molecular mass, we just have to add up the individual atomic mass. So in this formula we have 3 M's, we have 4 X's. Remember that this whole XO4, which is sort of like a polyatomic anion, I suppose, is taken 4 times. So then whatever's outside of the parentheses, you multiply whatever's inside, so it's going to be X. There's one of them in the ion, and there's a total of 4. So you're going to have 4 X's. And then the last thing we have is going to be the oxygen. So we have 4 oxygens in each anion, but we have a total of 4 in the anion, so 4 times 4 is 16. So we'd have 16 times the atomic mass of oxygen. So we just have to make sure we use the correct number of each element and then sum up the atomic masses that correspond to them. So the atomic mass of M is 105. We're told that directly in the problem. It's a fake element, so you have to be given that. So that's the contribution from M. For X is 36. So that's the contribution from X. And then we have 16 oxygens, and for this one we have to go to the periodic table. This is a real element, so it's not given to us in the problem. And on the periodic table we see that the molar mass or atomic mass of oxygen is 16, pretty much exactly 16, which is enough precision for this problem, 16 AMUs for oxygen. So when we add all of those together, we get a pretty big number. We get 715 AMU. This was a numerical problem, so you would just enter in the number 715. Alright, so calculating molar masses, this was for sort of a fake compound with some fake elements in it, but same approach. We have to add up the individual atomic masses, and that's going to play a role in a lot of the problems that we do today, so this will be a piece of what we do going forward. So the next few questions are ones where it's basically mole conversions, but there's a little bit of a extra step that I didn't really cover directly in class that got some of us, and is one that we often forget going forward. So we're given different types of compounds, and we're looking for different molar quantities. And in this first one here, we have glucose, which is C5HW1, O6. That's the formula for it. And we want to know the number of atoms in 48 grams of glucose. All right. So I think for this problem, we have to really think closely about the definition of a mole. So if we're looking for a number of atoms, we remember that glucose here is a covalent compound, and so each molecule is going to have 6 carbons, 12 hydrogens, 6 oxygens, and we have to start with the mass that we're given, 48 grams, and figure out how to get to number of atoms. So it's going to be a series of steps. Now what we should immediately think of is if we're looking for number of atoms, we're going to have to use Avogadro's number, but we're not starting with the number of moles, we're starting with the number of grams. So in these types of problems, I would say, I'm going to use this phrase a lot going forward in stoichiometry also. When in doubt, convert to moles first. So we're going to convert this amount to moles by using the molar mass. So 1 mole of C5HW1, we have to find the mass of that, and that's going to again be the sum of the atomic masses. So the molar mass for C5HW1 is 6 times the atomic mass of carbon. We get all these from the periodic table. So carbon is 12. We have 12 hydrogens, which from the periodic table is 1.008 grams per mole for atomic mass of hydrogen. And then we have 6 oxygens, which as we just saw is 16 grams per mole. So the molar mass for glucose, let me get this number real quick. And we get 180.16 grams per mole. So that's the molar mass of glucose. Again, we have to use that to convert grams into moles. We're going to use 180.16 grams of C5H12O6 per 1 mole. We're going to divide by that so that grams cancel out, and we get into moles. Now this is moles of glucose, C5H12O6, and I think what many of you did was just do the next step here and then stop. So we're going to multiply by Avogadro's number, but remember that Avogadro's number gives us how many of the smallest pieces of that substance we have. So if we want to cancel out moles of C5H12O6 by multiplying by Avogadro's number, which many of you did, what we have to keep in mind is that there are 6.02 times 10 to the 23rd, and this is going to be molecules of C5H12O6. Okay, because remember, when we use Avogadro's number, it gives us the number of the smallest pieces, the number of fundamental particles for that substance. This is a covalent compound, so 1 mole of this covalent compound is going to have Avogadro's number molecules, entire molecules of C5H12O6. And then finally, though, what we're looking for is the number of atoms. So this is not the number of atoms, this is the number of molecules that we have. So we have to figure out how many atoms are in 1 molecule, and that comes from the formula. So C5H12O6, that's 6 plus 12 plus 6, which is 24 atoms in 1 molecule. All right, so this is the step, this last one here, that many of us left off. Now you could have also done these steps in different order. We could have said that there were 24 moles of atoms in 1 mole and then use Avogadro's number last, but same numbers either order we do it in. All right, so we're going to make sure that we account for the fact that we're looking for the total number of atoms here, so we have to multiply by 24 because there's 24 atoms in 1 molecule of this. And then when we multiply all these numbers across, hoping that I did it right and didn't mess something up here. This is always like a little bit like Russian roulette because I do these problems as I'm going through them, and if I make a mistake, you guys will see it at home and then laugh at me, and I'll have to deal with that for the rest of my life. So anyway, we get the right number here, 3.85 times 10 to the 24 atoms, which does correspond to choice C, so that would be the correct answer for this question. All right, so as I said, last step here, we have to account for how many atoms are in a single molecule because Avogadro's number in a covalent compound would just give us the number of molecules, not the number of atoms. So that same concept is going to come up on the next 2 problems as well. So this is a very similar type of question. Here we have 27.5 grams of chloroform, which has a formula CHCl3, and we want to know the number of chlorine atoms, okay? And then this is one of those where we have to take the log of the answer and all that stuff. All right, so what we're going to do here is we're going to look for, again, we write down what we're looking for, which is number of chlorine atoms. And we're going to do a series of conversions until we get there. So we're going to start with 27.5 grams of CHCl3. So just like on the last problem, if we're looking for number of atoms especially, we have to go through moles. So we're going to convert this to moles first. And then for that we use the molar mass, which is the sum of the atomic masses. So I'm not going to go through that calculation, but it's 12.01 for carbon, 1.008 for hydrogen, and 3 times 35.45 for chlorine. So the molar mass of this actually is 119.37 grams per mole. So we're going to divide by that to cancel out grams and convert to moles of CHCl3 chloroform. And then again, if we just do Avogadro's number, that's going to give us, this is another covalent compound, so 6.02 times 10 to the 23rd That's going to be molecules of CHCl3. And this is where I think, as I'm going to emphasize over and over again, very careful labeling of all of your quantities, all of your units is going to be extremely important in this part of the course. We have to know exactly what these numbers mean so we know how many steps we have to do. So that gives us the number of molecules of CHCl3, Avogadro's number again telling us the number of the smallest building blocks for that compound. And then what we're going to do is, once again, we're looking for number of chlorine atoms. So we go to the formula, we see that our formula has 3 chlorine atoms, so there's going to be 3 chlorine atoms in one molecule of CHCl3. So then when we multiply that across, we get 4.160 times 10 to the 23rd chlorine atoms. This problem wanted us to take the log of that answer, so the log of that is going to be 23.619. Alright, so that's the number that we enter into Blackboard. Okay, so again, very similar series of steps as the last time. This time we weren't looking for the total number of atoms, we were just looking for one type, chlorine, so we just had to look at the formula and see how many of those were in the chemical formula. Alright, next problem here, similar concept, but now we have several different quantities, and we're looking for the greatest number of atoms in these different chemical samples. So we have helium, H2, potassium, H2O, KMNO4, and so on. We're going to figure out which one has the greatest number of atoms. Now, unfortunately, there's not a great shortcut for this because we have to basically calculate out all of these. So let's go through all of these and see which one has the greatest number of atoms. There's no easy way to identify this because they're all different quantities and different substances. So we have to go through the steps like we've been doing. So for choice A, we have 1 mole of helium. So helium is just a monoatomic gas. It's just made up of helium atoms. So if we want to find the number of atoms in this, we just need to multiply by Avogadro's number. 6.02 times 10 to the 23rd helium atoms in 1 mole. And we just get Avogadro's number. So this has 6.02 times 10 to the 23rd atoms. Alright, so this is just 1 mole of an element, so by the definition of a mole, it would have that many atoms. Now, if we go to choice B, though, here we have a diatomic element H2. So if we have 0.60 moles of H2, and we multiply by Avogadro's number, that's going to actually give us the molecules, not the number of atoms. So this is going to give us Avogadro's number of H2 molecules in 1 mole of H2. But then to get the number of atoms, just like we did before, our compound is H2, so there's going to be 2 atoms per each molecule. So if we want the number of individual atoms, we have to multiply this by 2. And this time we get 1.2 times Avogadro's number. So we get 7.2 times 10 to the 23rd atoms. Alright, so that one's a little bit bigger, so we can cross out choice A because B is larger. If we go to choice C, we have 20 grams of potassium, which is the atomic symbol K, and this is the same type of calculation we did before, where we start with grams, we convert to moles first by using atomic mass. So 1 mole of potassium from the periodic table has a mass of 39.1 grams. So remember, for elements, we just use the atomic mass to go from mass to moles, so we don't have to add any extra steps in there. This gives us moles of potassium, then we use Avogadro's number to figure out how many potassium atoms there are. And so this time it's going to be about half a mole, so a little bit less. So this is going to be 3.1 times 10 to the 23rd atoms. So that one's smaller, so we can get rid of choice C because that's smaller than choice B. We're looking for the greatest number, so we just have to keep the one that's the largest of all these. So choice D now is 8.5 milliliters of H2O. This has a concept that we haven't really covered yet, but I believe it was in the review chapter, so you were more or less expected to know this already. if we have milliliters of water, remember that we can go between volume and mass by using density, and the density of water is 1. That's the only density you'll ever have to memorize, is just the density of water, which is 1. So if we want to go from milliliters to grams, we use 1 gram of water is 1 milliliter. So that doesn't change the quantity at all, it just changes the units. So we have grams of water, and then same series of steps that we've been doing, we're going to use the molar mass and Avogadro's number to figure out how many molecules and atoms. So we use molar mass first. 1 mole of water has a mass of 18 grams. That's again the sum of the atomic masses of H2O. That's moles of water. We use Avogadro's number to get us how many molecules there are. It's a covalent compound, so Avogadro's number doesn't give us atoms this time, it gives us number of molecules. And then finally, if we want the number of atoms, we have to do one more step. H2O, the formula is 2 hydrogens, 1 oxygen, so there's going to be 3 atoms per 1 H2O molecule. I didn't spell that right, but who cares? So when we multiply this across, a lot of steps in this one. We get 8.5 times 10 to the 23rd. So that's our largest so far. That's larger than 7.2 times 10 to the 23rd, which is what we got for choice B. So far choice D is our largest. We have to do the last one, which I ran out of room for. But for choice E, it's the same steps we just did for water, but a different compound. So we have 22.6 grams of KMnO4. We use molar mass to figure out how many moles that is. So that's going to be the sum of the atomic masses for KMnO4 will end up being we get 158 grams per mole. Avogadro's number gives us how many formula units there are. This isn't really a molecular compound, but it's the same concept. So that's how many formula units, and then the number of atoms in KMnO4, we have 1 potassium, 1 manganese, and 4 oxygen, so that's 6 atoms per formula unit. So what we end up with is 5.2 times 10 to the 23rd. So even though this had the largest mass, or a larger mass anyway, than the water sample, it has less atoms because the molar mass is so much larger. So that's smaller than the one for choice D, so we get choice D. So a lot of steps in that question to get all these different answer choices. You may have been able to save some time by just calculating moles of atoms, because again, moles would just be multiplied by Avogadro's number. But if you really want to know the number of atoms in these samples, those are the steps that you do. You figure out which one is largest, and that ends up being choice D in this case, so we can get rid of all the rest. They're all smaller than that. Alright, moving on to the next one then. We have a single atom of element Q has a mass of 3.95 times 10 to the minus 22nd grams. What is the name of the element Q? So whenever we're trying to identify unknown elements, typically the way we're going to do that is we're going to find the atomic mass, because there really aren't any mole relationships that allow us to get the atomic number, which is the number of protons. That would unambiguously identify it. But if we get the atomic mass, we can look at the periodic table to figure out what that element is, and that's going to be the grams of the element in 1 mole of that element. And so there's a couple ways that we can approach this question, but essentially if we know the mass of one atom, we know that there's 3.95 times 10 to the minus 22nd grams per atom. We just have to convert that to grams per mole. All right. So the number of grams in 1 mole would be, if we have 1 atom of Q, we want to convert that to the number of moles of Q, so that's going to be, we divide by Avogadro's number. So 1 mole of Q would have 6.02 times 10 to the 23rd atoms. So that's how many moles of Q we have, and then we know from this given information that we have, sorry, I'm going to do this a different way because I screwed this up. Alright, so sometimes, as you saw what I just did, you get into a dead end where the units don't work out and you get confused yourself, so you just have to reevaluate and start over. So let's do it this way. Let's find the grams and then let's find the number of moles. So we have the grams is going to be here, 3.95 times 10 to the minus 22nd grams in 1 atom. If we have 1 atom, then we can find the number of moles in 1 atom. So that's going to be 1 mole of Q is going to have 6.02 times 10 to the 23rd atoms. So if we divide by Avogadro's number, that gives us how many moles of this element we have in 1 atom. So we just take the inverse or the reciprocal of Avogadro's number. So we have 1.66 times 10 to the minus 24 moles. And then we just divide the two. So the atomic mass is grams per mole, so we know that 1 atom has a mass of 3.95 times 10 to the minus 22nd grams. We know that 1 atom corresponds to 1.66 times 10 to the minus 24 moles. So then dividing the two gives us grams per mole, the number of grams in 1 mole, which is what the atomic mass is defined as. So when we divide these two, we get 237.9 grams per mole. And then if we go to the periodic table, we have to figure out which element is closest to 237. We're actually told in this problem that it's uranium. So in the periodic table for all these elements, we find that U, which is way down here, has an atomic mass of 238. That's clearly the closest to what we got, which is 237.9. So the one that works is choice D, uranium. All right. The rest of these all have much smaller molar masses than 237.9, so that couldn't be the correct answer for any of those. Alright, but again, for unknown element questions, there's one other one we're going to do later on. You typically want to find the atomic mass by finding the number of grams, which is in this case given to us, and then find the number of moles, which in this case we had to use, down here, Avogadro's number to figure out number of moles. Alright, back from an unscheduled commercial break because of a power outage in my building, although my tablet was on battery, so that didn't affect anything. Let's get back to it. Alright, so this question here, we have a metal oxide with a formula M2O contains 11.18% oxygen. That should be by mass, so that's how the question was worded. Type the symbol for the element represented by M. Okay, so this is the same type of question. We have an unknown element here, and so anytime we have an unknown element problem, there's going to be a few in this section, and then a few that we'll see later on, I think in chapter 7 or so, or chapter 8, they come back in a different format. So anyway, we have these unknown element problems, and we're going to typically do that by looking for the atomic mass of that unknown element, and that will help us identify the elements. So it's going to be the grams of the element, in this case M, divided by the moles of atomic element of the element M. Alright, so grams per mole. Alright, so we have to figure out what both of those quantities are. We don't really have either of them directly in this problem, but we do have a mass percent. So if we assume that we have 100 grams of the compound, whenever we have percentages, we can assume 100 grams to make our lives easier. So if you have 100 grams of M2O, we know that from the mass percent we have 11.18 grams of oxygen, and that means the rest of that 100 grams has to be the element M, so 100 minus that. So that would give us 88.82 grams of the metal M. So that's how many grams of metal we have in 100 grams of the compound. And now we have to figure out how many moles of the metal are in there. Alright, so again, we don't know the identity of M. That's what we're looking for in this whole problem, so we can't just use atomic masses to figure out moles. But we do know the identity of the other element, oxygen, and we know from the formula the ratio between metal and oxygen. M2O tells us that there's 2 moles of metal for every 1 mole of oxygen. So to find the moles of the element M, we start with the element that we know, which is oxygen, 11.18 grams of oxygen. We use the atomic mass to figure out how many moles of oxygen there would be in a 100-gram sample. So the atomic mass of oxygen, as we've used a few times, is 16. So that gives us moles of oxygen. What we need, though, is moles of M. That's what we're looking for to put in the denominator here. And so the moles of the metal are going to be related from the formula. So if we have 1 mole of oxygen, we have 2 moles of M, because it's M2O. Alright, so we're going to divide these and multiply across. So we get 1.398 moles of metal. So we're going to divide that by 1.398 moles. That's how many moles are in 100 grams. And when we divide those across by each other, we get 63.56 grams per mole. So I have to figure out which element has an atomic mass closest to 63.56. So we go back to the periodic table. They're going to typically be in order, so we go across. Finally here we see that copper, 63.55, is really close to the atomic mass that we calculated for our unknown metal. So that means we would identify the unknown metal as copper and just enter in this symbol into Blackboard for our answer. Alright, so another type of unknown element problem where this time we had to use the definition of mass percent to figure out how many moles of metal we have and how many grams we have, and then divide the two to get atomic mass. Alright, we're getting close to the end, so we have 3 more to go through. Alright, so just 2 more. Alright, so this one here, we did pretty poorly on it, but it turns out that this is actually a Chapter 1 problem, so I think we just kind of assumed it was harder than it was, or maybe forgot some things that we learned a while ago. So here we're talking about mass percent again, and we have a mineral that has lead and sulfur, so some sort of lead sulfide mineral, and we have analysis indicating that 3.65 grams contains 1.3 grams of lead. We want to know what is the mass fraction of sulfur. So we talked about mass percent before, which is the mass of one of the elements divided by the mass of compound times 100. Here we're just looking for mass fraction though, so we have to make sure we keep the definitions straight. So for mass fraction, we don't actually multiply by 100, we just take the ratio, the mass of the element, whatever element we're talking about, divided by the mass of compound. It's just a ratio. So the mass fraction would be between 0 and 1, whereas mass percents can go all the way up to 100 because you're multiplying by 100. Alright, so that's mass fraction. Here we're looking for the mass fraction of sulfur. So we need the mass of sulfur divided by the mass of compound. So we're not given the mass of sulfur, but we are told that we have 3.65 grams of the compound. And then the mass of sulfur, though, we know that we have 1.35 grams of lead, 1.3. So 1.3 grams of lead, which is symbol PB, although you don't need to know that for this question, plus the mass of sulfur is going to be equal to 3.65. So again, by difference, we can figure out that the mass of sulfur is just 3.65 minus 1.3, which is 2.35. So that's how much sulfur we have, so then we divide 2.35 grams by 3.65 grams, and that ratio gives us the mass fraction of sulfur, which is 0.644. Okay? Alright, so that was how we handled that problem. That was really just a definition of mass fraction. We didn't know anything about moles to do this one, so I think many of us just thought a little bit too deeply about this one, more than we needed to do. Alright? All right, last one is determining molecular formula given mass percents. So we have a compound that contains carbon and chlorine, and we're told the mass percentages of each. So again, for mass percent problems, we assume we have 100 grams of the compound so that the percentages just become mass amounts. We want to determine the empirical formula and the molecular formula. Given that the molar mass is 237, type the molecular formula in the space provided. Alright, so the first thing we do in these problems is we convert. We assume 100 grams of compound. As I said, we're talking about mass percents here, so that's the convenient way to do things. Alright, so 100 grams of compound, we want to look for the moles of each element then. So the moles of carbon is going to be, in 100 grams, you have 10.13 grams, because it's 10.13% by mass. And then we use atomic mass to figure out the moles of that element. Atomic mass of carbon from the periodic table is 12.01 grams per mole. So we divide by that to get moles of carbon. And we get 0.843 moles of carbon. Then we're going to do the same thing for chlorine. We have 89.87 grams of chlorine. The rest of our 100% will be chlorine. And then from the periodic table, the atomic mass of chlorine is 35.45. And so when we divide those two, we get 2.535 moles of chlorine. So to find the empirical formula, we just need to find the smallest ratio of those two numbers. And so we have carbon with 0.843, chlorine 2.54. We don't have to be that precise with these. We divide both of them by the smaller of the two to get it to a small ratio, or simple ratio I should say. And when we divide those two, we get CCl3, so basically exactly a 1:3 ratio. So that's our empirical formula. Now to find the molecular formula, though, we have to take the empirical mass and compare it to the molar mass. So the empirical mass, which is just the mass of 1 mole of the empirical formula, is going to be the mass for carbon, the atomic mass, which is 12.01, 3 times 35.45. For chlorine, and so our empirical mass is 118. We don't have to do that precise here. And then if we take the molar mass, which is 237, divided by the empirical mass, we're running out of room, so I apologize. We have 237 for the molar mass. That's given to us in the question. Remember, if we're going to find molecular formula, we have to have this additional piece of information. The mass percents can only give us the empirical formula, the smallest ratio. We divide the two. Why won't it let me write today? Come on. Alright, so 237 divided by 118, and if you're a math wizard, you can already tell that that's pretty much 2. So that means our molecular formula is 2 times the empirical formula. So it would be C2Cl6 for the molecular formula, and that's what we would enter in to Blackboard in this case, C2Cl6. Alright, so that takes us to the end of this week's review. If you have any other additional questions or want any clarification on these problems, I welcome you to contact me. And we're going to keep going in this week with a lot more of problems that involve mole conversions, specifically getting into stoichiometry, where we're dealing with chemical equations, chemical reactions as part of the issue. All right, I'll see you guys in class this week, and have a good rest of your day.